Okay, hello everybody. We are glad to welcome today Olivier Tercieux from Paris School of Economics. Olivier is going to present a paper entitled Optimal Queue Design with Yeon-Koo from Colombia. We also have the pleasure to welcome Yeon-Koo today and to welcome Refael Hassin from Tel Aviv University as a discussant. Well, I don't think I need to present longer Olivier, Yeon-Koo, and Refael, so we all know their substantial contribution. Thanks a lot for the three of you for being with us today. Before to start, let me remind quickly the rule and the procedure of the seminar. So as usual, Olivier will make some breaks at some relevant moments. And during these breaks, you can unmute yourself and ask your question. Actually, Yeon-Koo will reply to your question in the chat. So do not hesitate to ask your question directly in the chat. In case you don't have a stable internet connection, I will put in a few minutes in the chat a link for the slides that you could download. And be aware, as usual, that the talk is recorded. Okay, Olivier, Yeon-Koo, and Rafi, thanks again for being with us today. We are really happy about it, and we are really looking forward to your talk, Olivier. So I'll give you the screen.
Okay, thank you very much, Olivier. Thanks for having me. So I'm going to present this joint work with Yeon-Koo, which is about mechanism design and more specifically how we can optimally design a queuing system. So let me give you one slide of introduction. So it's well known that waiting in line is a very common phenomenon in everyday life. There are studies which evaluate the time you spend on average in your life waiting to 6 months for things like schools, hospitals, post offices, call centers, and so on. There's a branch of math which studies queuing and study specifically waiting lines and how queues forms, which is called queuing theory. The goal of this literature is to try to understand the determinants of a queue length in the long run, typically, and what determines also the waiting time of agents who are participating in these queues and are waiting in the queues. There's a subfield of queuing theory called rational queuing, which studies the agents' incentives to join a queue. So typically the agents are going to trade off the waiting time that they have to incur in order to get served with whatever they can get if they don't join the queue, meaning with their outside options. And so one goal of this literature is to try to understand what is the equivalent queue length and how it compares with what would be socially optimal. However, there is no systematic design treatment, to the best of our knowledge, where you would try to write down, like what we do in mechanism design, you would try to write down the designer's problem, so who tries to maximize some objective subject to incentive constraints. And so this is what we're trying to do in this paper. So instead of trying to give you the overview right now of the results, let me jump right away to the model. And it will help me later on to give you the overview and also try to connect our results to previous results in the literature. So let me jump right away to the model. So it's going to be a queuing model with general Markov process where time is going. So it's going to be a dynamic model where time is continuous. It runs from 0 to infinity. Agents are going to arrive randomly to a queue in order to receive service. More specifically, at each point in time, assuming that you have k agents currently waiting in the queue, an agent is going to arrive to the queue according to a Poisson process at rate lambda k, where this rate may depend on the number of agents who are currently waiting. Okay, I'll come back to this in a minute. But so agents arrive according to this Poisson process with rate lambda k, where k is the number of agents in the queue. Similarly, agents are going to be served. Agents waiting in the queue are going to be served according to a Poisson process again at rate mu k, where again this service rate may depend on the number of agents in the queue. So our primitive process, our primitives, what we will call a primitive process, is going to be a pair or a lambda of which is a collection of arrival rates for each queue length k, and mu, which is a collection of arrival rates for each queue length k. So this is going to be our primitive process. And we're going to make a number of assumptions on this primitive process. The first one is without loss, actually. We're going to assume that mu k, this service rate, is an increasing function of the number of people in the queue. And so the idea, why is it without loss? Simply, if you interpret mu k as the maximum service rate that for an agent who belongs to a set of k agents, then whatever you can do with k agents, you can also do it with k plus 1 agents. And so the service rate must be increasing in the number of agents in the queue. We're going to make more substantive assumptions later on. I mean, still mild, but this one is, we see it as without loss. There are a bunch of examples that are particular cases of the model we're proposing. One is the textbook example in the queuing literature, which is called the MM1 Queuing Model, where the arrival rate does not depend on the number of agents currently in the queue, and the service rate also does not depend on this number of agents in the queue. So one way to see this model is just that you have agents arriving to a queue according to a Poisson process lambda with rate lambda, and there is one server, and one of the agents in the queue is going to be assigned this server, and then he is served at rate mu. So this is a textbook example. There are generalizations of this model. The MMC model is one of them, where instead of having one server, you're going to have C servers, where C is an integer. Again, arrival rate does not depend on the number of agents in the queue, but now the service rate may depend on the number of agents in the queue. And how does it work? So let's say C is 3, for instance, to make things simple. Then if you have one agent in the queue, well, this guy is going to be assigned one of the 3 servers. And so with rate mu, this guy is going to be served. And if you have 2 agents in the queue, then each of the 2 agents is going to be assigned one server, one of our 3 servers. And then the service rate in that case becomes 2 times mu. When you have 3 agents, it's going to be the same thing. It's going to be 3 times mu. And after that, our servers are busy. And so service rate is going to remain at 3 times mu for larger queue lengths, okay, for when you have more than 3 agents in the queue. So in this model, service rate is first linearly increasing and then flat. So it's an increasing concave function. So we also consider dynamic matching model, which was one initial motivation of our paper. I'm going to be very informal here, but think of this model as models where you have an agent who arrives in the system according to some process, and then this agent effectively joins a queue if and only if this arriving agent is incompatible with all agents currently waiting in the queue. So if he's compatible in some sense, if he's compatible with one of the agents in the queue, those guys will be matched. And so the arriving agent does not join the queue. But if he's incompatible with all agents in the queue, then this guy joins the queue. So it's a model where arrival rate depends on the number of agents in the queue. And more specifically, the arrival rate is going to be a decreasing function of the number of agents in the queue, with the idea that as the queue length increases, the likelihood that the arriving agent is incompatible with all agents in the queue is actually decreasing. Okay, when you have more and more agents, it's more likely that you're going to be compatible with someone in the queue. So lambda k is decreasing in k in these models, and mu k, the service rate, is increasing in k. And the idea is the same. The likelihood that the arriving agent is compatible with someone in the queue is increasing with the queue length. And so someone is going to be served. So the rate at which someone is served is actually higher when the queue length increases. Okay, so these are models where, again, arrival rate is going to be a decreasing function of the queue length, and service rate is going to be an increasing and concave function of the queue length. I haven't been very formal here, but the models that are in the literature have this property that mu k is actually increasing concave. So these are 3 possible examples which are particular cases of our general Markov processes or our primitive processes that we define. And I'm going to sometimes assume that the primitive process is what we call regular. We see this as a very mild condition. So let me describe what it is. So in addition to assuming that this service rate is increasing, I'm also going to assume that it's concave, which, as I said already, was satisfied by all the examples I gave you before. And beyond this, we're also going to assume that the arrival rate does not increase faster than the service rate when k increases, when the number of agents in the queue is increasing. Okay, so this is kind of a technical condition, but all the models we know of satisfy this condition. So for instance, all these conditions are trivially satisfied in the MM1 model, where the arrival rate and service rate do not depend on the number of agents in the queue. For the MMC model, as I said already, service rate is actually first linearly increasing and then flat, so it's an increasing concave function. So this condition is satisfied, and the arrival rate does not depend on the number of agents in the queue, meaning that this left-hand side is just 0. And given that the service rate is increasing in k, the number of agents in the queue, this right-hand side is actually positive. So this condition is also satisfied. In dynamic matching model, it's the same story. Again, service rate is increasing concave, so this first condition is going to be satisfied. And as I said, the arrival rate is a decreasing function of the number of agents in the queue. So this term on the left-hand side is going to be negative, and this term on the right-hand side is going to be positive, just because, again, service rate is increasing in k. So what I want to say is all models, this assumption that I'll sometimes have to assume in order for our result to hold is actually mild in the sense that, again, all the models we know of satisfy these two assumptions, this assumption, so this regularity assumption. So now let me talk about the preferences of agents in our model. So we have three parties, let's say, in our model. One is individuals, so those people who actually decide to join the queue, potentially decide to join the queue, and wait to get served. The service provider is going to be one additional party, and the designer. So we are going to consider a very standard queuing model where you have homogeneous preferences with linear waiting costs. And so the utility of an agent who gets served after waiting for a period of time of t is going to be given by v, the utility of service, minus his waiting cost, which is going to be just t, so the time he has waited to get served, times the per period cost of waiting, cap c. Okay, so this is going to be the utility of an agent to get served after waiting for a period of time of t. So these individuals will trade off their utility of joining the queue with what they can get with their outside option. And so I'm going to normalize the value of the outside option to 0. So this defines the payoffs for the individuals. Now, but what about service provider? It's going to be very simple. I'm just going to assume that each time service occurs, so each time an individual in the queue is served, the service provider gets a flow payoff of R. And finally, the designer's objective, I'm going to be informal at this stage, it's going to be a weighted sum of the service provider's payoffs and the individual's payoffs. I'm going to describe this more formally later on, but let me take this, let me stick to this at the moment. The designer's objective is a weighted sum of service providers' payoffs and individual's payoffs. Given this objective, what are the instruments of the designer? We're going to allow for 4 instruments. And one is going to be the entry rule, which essentially, which is denoted by x. X is a collection of xk, where xk is a number between 0 and 1, and k is, again, k is the queue length. So what is xk? Xk is, given that the queue length is k, this is a likelihood that the designer allows an arriving agent to join the queue. So with probability xk, this guy will be allowed to join the queue. With the complement probability, is going to be turned away. Okay, so the designer can withhold service and just turn away agents potentially. So this is one instrument he has. You could think of this as, instead of saying the designer allows agents to join the queue, you could think of this as the designer is going to, with probability xk, the designer is going to recommend agents to join the queue. And we'll impose incentive constraints, which will ensure that, indeed, whenever agents are recommended to join the queue, they should be willing to join the queue. So with probability xk, the designer is going to recommend an agent, an arriving agent to join the queue when the queue length is k. Okay, so this is one instrument. And one simple policy is just I'm going to limit the queue length to some number k, beyond which nobody will be allowed to join. So all agents will be turned away if the queue length is exactly k. And below this k, agents will be allowed to join. So this is one possible policy where the designer will just cap the queue length. So this is for the entry rule. Now the exit rule is going to be denoted by y. And y is going to be a collection of ykl for each queue length k and position L. So I haven't defined what a position for an agent is. So this reflects basically the time that an agent has been waiting in the queue. And so an agent has position 1 if he's the agent who has been waiting for the longest time. He has position 2 if he's the agent who has been waiting for the second longest time, and so on and so forth. So then ykl is the rate at which an agent in position L is going to be removed from the queue when the queue length is actually k. Okay, so this is an instrument which allows the designer to potentially remove agents from the queue. So I've defined this entry rule, this exit rule. Now I need to define the two additional instruments that are very important for us. One is the queuing rule, and the other one is information rule. And the queuing rule is going to tell you, upon service occurring, who is going to be the guy in the queue who's going to get served, in a sense. So let me describe the queuing rule and the space of queuing rules that we allow in this paper. So QKL is going to be the rate at which an agent in position L is going to be served when the queue length is kept. I'm going to impose that the queuing rules must be feasible and work conserving or non-wasteful, which simply means that if I take, so feasibility means that if I take a set, so let's say the queue length is k, you currently have k agents in the queue, and I take a set of j agents in the queue, then you have, if I sum up their service rates, the service rates of these j agents, then it must be smaller than mu j, the maximum they can get when you have j agents in the queue. Okay, so this is just essentially feasibility. And work conserving means that if the queue length is k, and I sum up the service rates of all those agents in the queue from position 1 to k, then this must be exactly equal to mu k. Okay, so there is no waste. And so this is the second property we will impose. And so the designer will be allowed to use any possible queuing rule in this space of queuing rules that must be feasible and work conserving. So this is a large space, and you can think of many existing rules that belong to this set. For instance, first come, first served is one of these rules. So what is first come, first served in our environment? It's a rule where the guy who has been waiting for the longest time, so the guy who is in position 1, the designer will maximize his service rate. Okay, so this means that given feasibility, his service rate will be mu1. This is the highest service rate that he can get. And then the guy in second position will get the highest service rate, given that we already maximize the service rate of the guy in position 1. So this means that he's getting mu2 minus whatever, is getting mu2 minus whatever the guy in position 1 is getting, meaning mu1. Okay, so the guy in position 2 is going to get mu2 minus mu1. And in general, the service rate is going to be defined by this formula. So the guy in position L is getting served at rate mu L minus 1. If you come back to the MM1 model, again, the simplest model where the service rate and the arrival rate do not depend on the queue length, and you have a single server, the model I described before, then you get what you would expect, meaning that the guy in position 1 gets all service, is served at rate mu, and all the other persons are served at rate 0. They have to wait for the first guy to be served before being served. Last come, first served is actually, in a sense, the other way around. So what you want to do on the last come, first serve is, given that the queue length is kept, you try to maximize the service rate of the agent who is in position k. So meaning the guy who arrived the most recently. So this guy will get served at rate mu1, and then the guy in position k minus 1 is going to be served at rate mu2 minus mu1, and so on and so forth. So it's kind of the opposite of first come, first served. And again, in the MM1 model, this gives you exactly what you would expect. Given that the queue length is k, if the position of an agent is L equal k, so he arrived the most recently, then he served at rate mu. And for the other positions, service rates is just 0. So these are two rules that are discussed in particular in the literature and are part of the rules that we are allowing. One more rule is service in random order, which essentially you could think of as upon service occurring, the guy in the queue is going to get served is randomly selected. So this means that the service rate is not going to depend at all on your position. And in a sense, this means that the service rate is shared equally among agents. So this means that this QKL is just equal to mu k divided by k. Okay, all agents get served at the same rate given the queue length, given that the queue length is k. So these are three possible rules, and again, they belong to the set of queuing rules that we're allowing. Any questions on this part or? Okay, so I described the entry rule, the exit rule, and the queuing rules. I have a fourth instrument, which is actually the information rule. Let me describe it briefly. I'll be a little bit informal, but I think it's going to be pretty clear what it is. So an information rule is a collection of IT for each time t, where IT represents the information that an agent gets on the state, which he cares about, meaning the queue length and his position in the queue, after he stayed for a period of time of t in the queue. Okay, so you could imagine that what the designer will do is, after an agent has stayed for a period of time of t, he's going to send signals to the agent which are correlated with the state. And this is how people are going to be learning about the state. And so you could think of IT just being like this, just sending signals on the state that are correlated with the true state, with the states. You can think of many possible information rules. Two specific cases are full information, which are often assumed in the literature. Full information is just that when you join the queue, you have, you're told what the queue length is, and hence you know what your queue position is. And then as time passes, you still get perfectly informative signals, which are going to tell you exactly how the queue length evolves and how your position in the queue evolves. So this is the full information. You get exactly the true state. The information rule gives you exactly the true state. And the no information rule beyond recommendation is one rule that I'm going to talk about, where through the information rule, the agents won't get any informative signals, but they will get informations only through recommendations. What I mean by this is, let's think about the case I gave you before, where the entry rule for the designer is to fix a cap on the queue length. Let's say beyond cap k, beyond 10, let's say, nobody is allowed to join the queue. Then if you're recommended to join the queue, you learn something on the queue length. You learn that the queue length is smaller than 10 here in this example. And in general, given the policies, so given the entry rule and the exit rule, the recommendations will give you some information on the state. So you learn information in this way through recommendations, but you don't learn any additional information. In particular, the information rule is not going to provide any information, informative signals, additional informative signals. So these are two specific information rules, but we are allowing for, again, a large set of information rules. So these are all the instruments of the designer. Again, the entry rule, the exit rule, the queuing rule, and the information rule. And then I'd like to give you another view of the results that we have. Before this, let me just give you one more piece of notation, or one definition. So first, if you fix an entry rule X and an exit rule Y, then this, together with a primitive process, is going to induce a Markov chain on the queue length. Okay, so the queue length will evolve according to a Markov chain, actually a birth and death process. And let me assume that there is an invariant distribution for this Markov chain. Let me denote it by P. Then I will say that P is generated by policy xy, meaning that if the designer chooses x and y, then the invariant distribution which corresponds to the Markov chain induced by x and y is going to be exactly p. Okay, so if the designer picks x and y, then for sure in the long run, for sure the invariant distribution will be p. Okay, now that I said this, the designer objective, you could think of it as is going to maximize a weighted sum of flow payoffs for the service provider and individuals. Again, I'll be more precise in a couple of slides. It will do this at the invariant distribution, so you could see this as a long-run objective. And this is going to be made subject to incentive constraints. So it will maximize this objective subject to incentive constraints. And here, incentives are going to be so that whenever an agent is recommended to join the queue, when he arrives, he's recommended to join the queue, then we want the agent indeed to have incentives to join the queue. And whenever an agent is recommended to stay in the queue, so he's not removed from the queue, then we want the agent to have incentives to stay in the queue. Okay, so these are the incentive constraints we will impose. They are one-sided. Very briefly, let me comment on this. They are one-sided in the sense that if an agent arrives and let's say he arrives, but the queue is already full, the queue length is the entry rule is so that the designer limits the length of the queue to 10. Then the arriving agent may be willing to join the queue, but we assume that the designer can withhold service, and so we can turn away the agent in some sense. And this is similarly for agents who are removed from the queue. This is simply assuming that the designer can withhold service and just not serve those agents that are removed, even though they may be willing to stay in the queue. In a sense, the designer can we don't impose the incentive constraint that those guys should be willing to leave the queue. Okay, so the only incentive constraints we impose is that when an agent is recommended to join the queue, he's going to be willing to do so. And when an agent is recommended to stay in the queue, he should also have the incentives to stay in the queue. Okay, so these are the incentive constraints, and this is one informal description of our problem. Two very brief comments. One is that we're going to have to think about how the belief of agents evolve, over their position in the queue. Because not being matched for a while may provide some information. You may update your belief if you're not matched on the queue length, for instance, but also because you get some information through the information rules. And so we have to think about what the prior beliefs of agents are, and we assume that the prior beliefs of agents are just given by the invariant distribution of our stochastic process. And second, maybe more importantly, that we care about dynamic incentive compatibility, meaning that we do care about the incentive of agents to remain in the queue. And this is often disregarded in literature. This is really critical for our argument, and this is going to be critical for identifying the optimal queuing policy in our environment. So really, the incentives to remain in the queue is going to be important and critical for what I want to talk about. In terms of a preview of the results, here's what they look like. So we have an optimal cutoff policy, which means that entry rule and exit rule will be fairly simple. So the exit rule will be extremely simple. We will never remove agents from the queue. The only reason why agents are leaving the queue is because they are served, but you never remove an agent who is not served. Okay, so this Y will always be 0, this exit rule. And the entry rule will be similar to what I described before as a cap, meaning there will be some integer cap k, beyond which agents will be turned away. They won't be allowed to join the queue, and below which agents will be recommended to join the queue. So entry rule and exit rule are going to be simple. And in terms of information rule, we'll have the no information rule as the optimal solution, meaning agents are not going to be provided any information beyond the information that they get through recommendations. And in terms of queuing rule, we end up with the queuing rule, which is first come, first serve. This is going to be the optimal solution. So also a fairly simple queuing rule, which is used in practice. So this describes the three first bullet points, describe the optimal solutions of the designer's problem. And on top of this, we show that first come, first serve is actually necessary for optimality in a rich domain sense, in the sense that if you take any alternative queuing rule, which differs from first come, first served, then you can find an environment, actually a MM1 environment, in which this queuing rule is not going to be optimal under any possible information design. So it's a sense in which this first come, first serve is uniquely optimal if you think in a large domain sense.
Can I ask a quick question about the no information is optimal result? My waiting time in practice may depend upon whether I know my likely wait. So if I'm told you're our 14th in line, we estimate you'll be served in 46 minutes. I know I can go get a cup of coffee, do some other work, and the waiting cost can be, this would be especially true if it was just online and I'm at my desk and can be productive. I'm assuming your no information result does not extend to that sort of environment.
So an environment again where
where waiting costs can be less if I have information, because if I'm told you're in line, you have every incentive to stay and told nothing else, then it's very costly because I have to always be paying attention.
Yeah, that's true. So the waiting cost in your case, you're not going to incur a large waiting cost if you know precisely. I mean, have some precise information on when you may be served. So no, that's true. This is not incorporated in this model. So, but you'll see the fact that it's no information at all may not be such a big issue. I think eventually what we want to say is that not releasing all information may help to achieve a better solution than under complete information. And once you don't release all the information, first come first served is going to be the best rule. So I'm going to explain this later on, but I think eventually we don't want to take too seriously the fact that we provided really no information. There are many arguments, including yours, which may make more valuable the fact that you get some information, but I think one of the main insights that we want to take from this paper is that not releasing all information may be better in terms of the objective you can achieve. And once you do this, you have to regulate agents' beliefs. It's a bit soon to talk about this, but you have to regulate agents' beliefs, and first come first serve does this better than other rules. So yeah, but I mean, for sure. Again, I don't think we want to take too seriously the fact that providing no information is really the best thing you can do. I can imagine many reasons why providing some information is actually valuable. But again, this is more like if you don't release all information, then you run into issues which have to see with how beliefs of agents evolve over time, and then first come first serve becomes critical to discipline the evolution of beliefs. Again, this is a bit soon, but I hope this is going to be clear in yeah, I hope this is going to be clear by the end of the talk. Any other question? No. Okay, so the link with the literature. So part of the literature is trying to optimally design queuing rules where the information rule is actually fixed. So I mentioned some papers. One famous paper, actually these two papers are famous. So now what now shows is that in the MM1 environment, when you have full information, meaning agents are informed about the queue length and their position, then first come first serve is suboptimal in the sense that the people have excessive incentives to queue. So the equilibrium queue length is going to be too long compared to what would be socially optimal, and the idea that when agents join the queue, they don't internalize the externality that they may exert on those guys who are going to be joining later on. And so first come first serve is suboptimal. This is one point in now, and Hassin showed that this is corrected by last come first served. In this environment, last come first served turns out to be optimal. So this is an environment where you have excessive incentives to to join the queue. You have other environments, like the one proposed by Jacob Leshno, where you have insufficient incentives to join the queue under first come, first served, again, assuming complete information. What Leshno shows is that this is, so you can improve on first come, first served by using zero, so service in random order, and he identifies an optimal queuing rule, which is called load independent expected wait, U. So all these papers are dealing with the optimal design of a queuing rule when the information is fixed to complete information. And you have other papers who actually do the other exercise, meaning that they fix the queuing rule to first come, first served, and then try to do some information design. So I listed some papers who do this. Basic point is that we are trying to handle both, we're allowing the designer to have both instruments simultaneously, meaning the queuing rule and the information rule. And by doing this, we end up with an optimal solution, which is fairly simple. And I think really one value in a sense of what we're doing is by enlarging the set of instruments, we end up with a solution which is extremely simple and actually used in practice, again, first come, first serve, where with policies like fixing a cap on the queue length. So this is one difference with these papers. Again, we allowing both for information design and queuing and queue design. We also consider dynamic incentives, which is really critical for what I want to talk about today, which again means that we thinking about the incentives of agents to remain in the queue, to stay in the queue whenever they are recommended to do so. And we consider a general primitive process which goes beyond the MM1 environment or MMC environment. So this is a very brief literature review. Let me go back to the designer's problem now and explain what's our methodology and be a little bit more precise on the designer's problem, what it looks like. So again, the set of instruments is going to be this quadruplet. So entry rule, exit rule, queuing rule, and information rule. So this is the set of control variables for the designer. And what he wants to do is to maximize the weighted sum of agents' flow payoffs at the invariant distribution P. Okay, by agents flow payoffs, I mean both weighted sum of service providers payoffs and individuals payoffs. Again, I'll be formal in the next slide. This is subject to a balance equation. So this is kind of a technical condition. You don't have to bother too much with this condition. It basically says that P here is actually generated by the policy X and Y. So the invariant distribution P is actually generated by the choice of entry rule and exit rule of the designer. And then more importantly, this is subject to incentive constraints, meaning that when agents are recommended to join the queue, they should have incentives to do so. And when they are recommended to stay in the queue, they also should have incentives to do so. Okay, slightly more formally, this is the objective of the designer. So he puts a weight 1 minus alpha on the expected flow payoff of the service provider. So Pk is the likelihood of state k at the invariant distribution. Mu k is the service rate, the rate at which service occurs when you have k agents in the queue. And then R is the flow payoff whenever service occurs. So this is the expected flow payoff of the service provider. And there's a weight alpha on the expected total flow payoffs of individuals, those who are in the queue. And so Pk again is the mass put by the invariant distribution on the queue length being k. When the queue length is k, service occurs at rate mu k, and in that case, V is the gain. What about the costs? So the costs are going to be C, and when you have k agents in the queue, you multiply this C by the number of agents. So this is the total. This is the expected total flow payoffs for individuals who are in the queue. Okay, so this is the objective of the designer, and then this is maximize subject to two conditions. Again, one is the balance equation, which tells you that this P is actually an invariant distribution given the choice of X and Y. Very briefly, so this is a characterization for birth and death processes of invariant distributions, which essentially tells you that so P pk, the likelihood of k at the invariant distribution, times bus rate, so the rate at which you move from k to k plus 1. So lambda k, someone arrives, and then this guy is allowed to join the queue. So you move with this rate from k to k plus 1. So bus rate times pk is equal to pk plus 1 times death rate. And so death rate is the rate at which you move from k plus 1 to k. And so you move from k plus 1 to k either because someone is served or because someone is removed from the queue. And again, this is also maybe more importantly subject to incentive constraints, which I'm not being formal, but it just tells you that for each time t, so t equals 0 means that the agent just joined, and t strictly positive means that the agent is already in the queue. Irrespective of the signal that the agent gets from the information rule, the agent will have incentives to stay in the queue or join the queue if t is equal to 0, meaning his expected payoffs are going to be higher than what he can get with the outside auction. So in general, this problem is fairly difficult to solve. In particular, the incentive constraints are complicated because you have to think about how beliefs evolve over time. And in particular, the way in which they evolve may finally depend on the queuing rule. So these are fairly complicated objects. And so the way in which we proceed to solve this problem is to first consider a relaxed problem. So the relaxed problem looks like this. The designer can only choose the invariant distribution P. By the way, very briefly, implicitly here, the designer can choose the invariant distribution because by choosing X and Y, he eventually is able eventually to choose an invariant distribution. By choosing entry rule and exit rule, he's able to choose an invariant distribution. So here I'm going to assume that the only instrument or the only control variable that the designer has is P. He maximizes the same objective, the subject to two relaxed conditions. So a relaxed balance equation. Briefly, if you come back to this condition, essentially what I did is just so xk is the probability with which an agent is allowed to join the queue when you have k agents in the queue. So this is between 0 and 1. So I'm fixing this to 1. So this increases. And I'm fixing all the y's to 0, so all removals to 0, and so this decreases. And so this is why we have this condition. And so this is a relaxation of the balance equation we had before. And more importantly, I'm going to relax the incentive compatibility constraint. So this is a very weak condition. It basically tells you that the expected total flow payoffs of individuals is positive. And you can show that this is actually equivalent to assuming that agents have incentives to join the queue whenever they are not informed, when under the no information policy. So this is our relaxed problem. And so we start by studying this relaxed problem and then explain how it connects to the initial exact designer's problem. Is there any question on this part? Can I clarify anything? Okay, so let me move on and give you the first result, which is about, again, this relaxed problem. And so in order to state the result, let me just introduce an additional definition. So a cutoff policy is going to be a pair of an entry rule and an exit rule, so that so the exit rule is always 0, meaning no agent is removed from the queue. And there is an integer cap k star, which is so that beyond this integer, so when the queue length is larger than k star, all agents will be turned away. So no agent will be recommended to join the queue and will be allowed to join the queue. And below k star, agents will be recommended to join the queue. More specifically, below k star minus 2, they will be recommended to join the queue with probability 1. And at k star minus 1, there may be some random rationing. So maybe xk is interior at k star minus 1, but other than that, but this is the only difference from what I described before as being a policy where you would have a cap. The only difference is that potentially here you have random rationing when the when the number of agents in the queue is k star minus 1. And so this is a cutoff policy. This is the definition of a cutoff policy. And so the theorem says if the primitive process is regular, actually we only need to have the service rate being increasing concave, then an optimal solution of the relaxed problem, P star, can be generated by a cutoff policy. So there is an invariant distribution, which is a solution of the relaxed problem, which can be generated by this simple cutoff policy. Okay, so it's just an intermediary step. It doesn't tell you anything about what the solution of the exact designer's problem, but it's just a first step, which is going to be useful to state the main result that we have. Yeah, again, there is under a cutoff policy, there is no need for removing agents. And you could think of the entry rule as essentially fixing a cap on the queue length, beyond which no one is allowed to join, and below which agents are recommended to join the queue. So here's the main result, which gives a solution to the exact designer's problem. So let me explain how what the result is. So first, fix a cutoff policy, x star, y star, which generates an invariant distribution, which is a solution to the relaxed problem. Again, this exists. You can actually find such a cutoff policy by the previous result. Now assume that the primitive process is regular. Then an optimal solution of the exact designer's problem is exactly this cutoff policy x star, y star. So this entry rule x star and exit rule y star, together with first come, first serve, and the no information rule, where again, this is no information beyond recommendations. Okay, so this is the main result, which we took a detour. We eventually went through the analysis of the relaxed problem. But by doing this, we are able to come back to the initial exact designer's problem and show that we have a simple solution to this problem. So is there any question on the statement or anything I can clarify? So if not, let me move on and explain how we prove this result. So there are two steps. By the way, it's kind of clear. It's clear that the value of the if we can show that incentive compatibility constraints are satisfied, it's clear that this should be optimal because it achieves a value which is the value of the relaxed problem. So this is going to be optimal. So what we need to show is that incentive constraints are satisfied under this cutoff policy, together with this the no information rule and the first come and first come, first served. So first, we show that agents actually have incentives to join the queue whenever they are recommended to do so. And this is very simple, and it's almost by construction here. And the reason is that if the designer uses this entry rule and exit rule, x star, y star, then we know that by assumption, this generates an invariant distribution, which is the solution to P prime, the relaxed problem. And then we know that P prime satisfies this relaxed incentive compatibility constraint, which, as I said before, is equivalent to giving incentives to agents to join the queue when they receive no information. So by construction, agents will indeed have incentives to join the queue whenever they are recommended to do so. And this is just by assumption on x star, y star. And so far, I haven't used anything about the queuing rule. And in particular, this first step holds actually irrespective of the queuing rule that you use. Now, for the second step, it's where dynamic incentive compatibility matters. And this is really where first come, first serve plays a role. So what we want to show is that for when an agent has stayed for a period of time of t, he does have incentives to stay in the queue. If he has not been served, he's still in the queue. Given that the optimal solution never removes agents, he must have incentives to stay in the queue. And then the question is, he had incentives to join the queue. The question is how beliefs evolves. are people becoming more pessimistic or not? For instance, how is the residual expected waiting time evolving over time? This boils down to this question, and you can imagine many rules which will fail dynamic incentive compatibility. For instance, just take 0, so service in random order. And let's assume that arrival rate is high, and we're using this rule. I joined the queue, and now I haven't been served for a while. Well, if I haven't been served for a while and arrival rate is high, then I'm going to start thinking that maybe now the queue length is much longer than what it was initially. And so if it is so, if I think the queue length is much longer than what it was initially, well, I'm competing with all those people who are waiting. So this means that my expected waiting time may have increased compared to when I joined the queue. And in that case, I may be willing to just leave the queue, and we know that this is suboptimal. So then this is one rule where dynamic incentive compatibility would be an issue, and so the goal is to show that this is actually not an issue under first come first served. And the reason why it's non-trivial is the following. So again, the question boils down to what happens after some elapse of time in terms of my residual waiting time. Is it the case that the elapse of time without being served is good news or bad news in terms of this residual waiting time, residual expected waiting time? So it's straightforward that it can be good news. And let me explain this, but this is the most simple force. It can be good news because conditional on the initial queue length, let's say when I joined the queue, there was 10 people in the queue, including myself. Then under first come, first served, well, my position in the queue can only increase, can only improve. So in particular, if my position was 10 when I joined, then it cannot become 11 or 12 by definition of first come, first served. So my position can only improve. And so this is a force which pushes my residual expected waiting time downward, right? So my expected waiting time will be smaller because of this force. But there's another force which is going to make me more pessimistic, which is that what I described here is conditional on the initial queue length. That's true that my position can only improve. However, my belief on my initial queue length may vary over time. And as time passes, I haven't been matched for a while. I haven't been served for a while. Well, maybe it's a signal that the initial queue length is much longer than what I initially thought. I thought with high priority it was 10. Now I haven't been matched for a long time. Well, maybe it's much longer than it was much longer than 10. And so this is a force which actually makes me pessimistic and drives my residual waiting time upward. Okay, so the question is what is the force which dominates the other? And what we show, the whole point of the proof in our paper is to show that under regularity of the primitive process, good news actually dominates bad news. Is there any question on this? So I think I need to rush a little bit. So let me move on and just explain. So I described the optimal solution of the designer's problem and some intuition for how the argument works. And let me explain why first come, first served is actually necessary in general. I mean, in a rich domain sense. So in principle, you can think of other queuing rules or information rules that may work. Intuitively, giving more information or non-trivial information is not going to be optimal. And this is actually a fairly simple, the intuition behind this is fairly simple. And I think there are many papers that use this type of intuition, previous papers. If you provide no information, then you pull the incentive constraints. And it's easier to satisfy, on average, the incentive constraints rather than pointwise. So if you provide no information, you pull the incentive constraints, and then you can achieve higher objectives. And so it's going to be easier to achieve an optimal solution in that way. So pulling the incentive constraints is really good. Now, so this is why providing non-trivial information is not going to be optimal. Now, if you take a queuing rule which differs from first come, first serve, you also show that it's actually suboptimal under any possible information design. in the sense that you can cook up an environment, actually an MM1 environment, in which this rule will fail to implement, will fail dynamic incentive compatibility under the optimal cutoff policy. And so if you come back to 0, I already gave an intuition, under 0, what happens is that as time passes, I'm going to be, if the arrival rate is large, for instance, if I haven't been served for a while, then I'm becoming pessimistic on my residual waiting time, and I'm going to be willing to leave the queue, even though I shouldn't do that at the optimal solution. And under any other queuing rule, something similar happens. If you take other queuing rules, it's going to be the case that given your position, as your position is 1, then the rate at which you're served is going to depend on the queue length. And once it depends on the queue length, a similar argument to the one I described for 0 applies. So the argument is much more involved in a sense, but I think the one of the basic intuition is this one. And so the theorem says, again, let me restate it. If you take any rule other than first come, first serve, then you can cook up an environment. And actually, we build a MM1 environment under which this queuing rule fails to be incentive compatible, in particular dynamic incentive compatible, when the optimal cutoff policy is used, and this under any possible information rule. So let me conclude. And so without information design, the designer's problem, we don't know what the solution is. We believe it's probably complex, and the outcome is certainly worse than what you can achieve with information design. I think the main point of the paper is if you allow for information design, then the optimal solution is going to be much simpler, certainly. And in our case, first come, first serve with no information is actually an optimal solution. As was already mentioned, you can imagine many unmodeled benefits of getting information on the queue position or on the expected waiting time. You can think of many arguments. One has been given. You can think about transparency. People may care about checking whether nothing strange happened if no one with a position better than worse than them has been served. So they may care about transparency, and getting some precise information is useful in that case. People may dislike being in the dark, or you can imagine other arguments. There may be competition among platforms, and providing no information in that case may be harmful because agents like to get accurate information. You can imagine plenty of arguments. As I said, I think our argument is as soon as you believe that not releasing all information may help to relax the incentive constraints and then achieve a bit higher objective, then you have to think about how beliefs evolve over time. And our point is that queuing disciplines actually can be used to regulate the evolution of agents' beliefs. And we show that first come, first serve is actually the best rule in regulating these agents' beliefs. I think this is all what I want to say. Thank you very much. I'm sorry that I've been a bit long. Happy to take questions or hear about Rafi, of course.
Thanks a lot, Olivier. I think we can move to the discussion of Rafi. So maybe Rafi, you can share your slides. And of course, after the discussion of Rafi, we can all stay and keep going to discuss, and so there is no time constraint for discussion. Rafi, we don't hear you. You have to unmute yourself.
Here. Okay. Now you're here?
Perfect.
Yeah? Yeah, all right. Okay. So I'm glad to be here to discuss this paper. I think it's a very good paper, very interesting, and it has many novel ideas. And I know the literature very well, so I can say it with confidence. So I chose some points that I want to discuss. I hope that I don't make big mistakes here and my understanding is correct. just an introductory paragraph about rational queuing. So it's a relatively new area. The first paper by Naor was published in Econometrica in 1969. But since then, there are very, very many research papers that belong to this area and very many applications in different domains. So the current paper has some novel ideas, and both from the modeling side and both from the solution approach, and the two main modeling extensions are written below. The arrival and service rates are state dependent. And the second one is that the server also gets some benefits from service that is not produced by transfer fees. It's in most of the literature, if the server gains something, it's from fees that are taken from the customer. So these are transfer fees, while here there is some benefit to the server that is independent of the benefit to the customers. I will discuss soon why is this important. Now, the model, one new property of the model is that it allows rejection of both customers when they arrive and both when they are already in the queue. You can tell them to abandon the queue. Now, this assumption does not exist in most of the literature, or maybe in all of it, because in most models, the solution becomes quite trivial if you allow rejection of customers, because like in Naor's seminal model, in most queuing models, when a customer enters the queue, there are negative external effects that other customers will have to wait longer, for example, and therefore customers want to join in many cases when the social objective says don't join. So the question usually is how to control the system, but without directly telling customers you are not allowed to join. So the question is, in this case, it's opposite, because I can control customers, tell them not to join, but I cannot control customers and tell them to join when they don't want to do it. So the interesting model is when there is excessive desire to balk from the model, to abandon the model, or there is not enough desire to join the model. And this is associated with positive externalities. When someone joins the queue and brings positive externalities, then in equilibrium, when individuals make individual decisions, not enough customers join. So this is the opposite of most models. Still, there are some models. For example, there is model mentioned here, N policy, where when the queue is empty, the server stops serving and only continues when the number of customers in the queue reaches some number, say N. This is called N policy. In this case, when I come to the queue, I want more customers to join the queue. Then, so they will activate the server sooner. And another case is something called the supermarket problem, or variations of it, when customers view, there are several queues, customers view several of the queues and choose the shortest one. This makes the whole system functioning more efficiently, and therefore there are positive externalities here. So sometimes I want customers to be more active, and I want to encourage them to come to the queue, and, well, not to come to the queue, but to inspect more queues. So in this paper, there are two assumptions that give rise to positive externalities. The one is that there are benefits to the server, not just to the customer. And customers tend to ignore the benefits that they give to the server, and therefore sometimes they are less enthusiastic to join the queue, and the server or the system wants to encourage them to join. And the other thing is that the service rate increases with the queue length. So again, my own interest after I joined the queue is that more others will join the queue, and then the service rate will be faster. But I will talk about this later when I discuss what is the meaning of first come, first queue here. First come, first served, and the second point may look different. So I want to make some comments about positioning this paper with respect to the literature. And mainly I will concentrate on the horse model. The horse model is a single server queue, and there is no power to reject. And the optimal behavior is a cutoff strategy. It's called usually threshold strategy, queuing or cutoff, both are the same. And the question is, how can I control the queue when I cannot reject customers? So one obvious solution is an entry fee. When I charge an entry fee, then less people will join the queue as I want. The current paper tries not to use monetary means. In this case, it may be subsidies, not just taxes, but we're looking for other means to control the queue. So as was mentioned, last come, first served. Again, it's a different meaning in general, but for a single server queue, or for an OS model, it's the same. I once proposed last come, first served. In this case, all arrivals join the queue, and the one who makes the decision is the one who arrived first and is now positioned last in the queue. And the main point is that the decision of the last one in the queue involves no externalities at all, because he's the last one, he will stay the last one, nobody else cares if he leaves or not. So his decision is identical to the social decision, and by imposing last come, first served regime, we don't have to do anything, the queue will behave in an optimal way. There are other ways, like a priority menu in the paper of Alperstein, where there are priorities, and each priority is associated with a price. The higher the priority, the higher the price. And if the prices are appropriate, then the customers will induce a last come, first served queue by choice. So it's not imposed on them, but they can choose the priority, and the way they optimally choose the priority is by always selecting a higher priority than everybody else in the queue, so we get last come, first served. Another paper by Aviv and Oz has slots, and customers, when they arrive, they can choose the slot that is closest to the head of the queue. And again, there is a last come, first served regime that is induced but by choice. I want to mention profit maximization because it leads to similar results to the current paper. So there is a server, and the server charges entry prices or service prices. And what is the maximum profit that is possible? So the maximum possible profit requires two points. Two things must be obtained. One is that the system will operate optimally, so it generates the highest possible benefit to society. And the second point is that all the generated welfare will go to the owner, to the server. So if these two conditions exist, clearly the server gets the most or the maximum that can be obtained from the system. And this goal cannot be achieved with a single price, but it can be achieved by dynamic pricing, so a price that depends on the queue length. It can be achieved by last come, first served, because when we have last come, first served, every arriving customer has the same expected benefit, so I can just charge a price equal to this expected benefit, and I get that the system functions optimally and all the benefit goes to the server. There is another possibility here, but the last one is the most interesting to our paper. It's how high-low information. So there is an optimal threshold. It's written here as an N star. And I just recommend, if I want to choose the language of the current paper, I recommend that customers join if the queue length is below N star. But I don't tell them what is the queue length. So this is exactly the no information case here with a recommendation. But the recommendation is just to join the queue or not to join the queue, or maybe just to join the queue. It is given when the queue length is less than the optimal threshold. And then I charge the maximal fee that customers are ready to pay when they are told that the queue length is less than N star. So in this case, again, they will join if the queue length is less than N star. They will not join if the queue length is longer than this, and all the benefit goes to the server. This is quite similar to the present paper, but the objectives in the present paper are quite different. So it's nice that you get similar results for a different model with different assumptions and different objectives. And there are some later papers that obtained similar results to this, mostly independent of. Now about the cutoff policy. So as we heard, the problem is to maximize the system welfare, and there are balance constraints that determine the probabilities, the state probabilities of the system, and there are IC constraints, and no fees are allowed. And the central question is first if a cutoff policy is optimal, because otherwise it's quite hopeless to find a simple solution. The fact that we prove, or the authors prove, that the optimal policy is a cutoff policy, then from this point on, everything is much simpler. And it's not trivial that this property holds. And actually, it's very easy to generate arrival rates and service rates such that customers will refuse to join a short queue because the service rate is very small, service is very slow, but they will be happy to join a long queue because the service rate there is very high, and you can keep the queue length from falling down by assuming that at certain point nobody joins. At certain point the service rate is zero. So the queue, it never becomes short, and then customers are happy to join long queue, but they don't want to join the short queue. So the authors define these necessary conditions, that the service rate increases in a concave way, and the arrival rates do not increase faster. And I think this is a very nice result to characterize necessary conditions for a cutoff policy to be optimal. Now, an important point that if I'm correct, then the authors missed this point and they should discuss it. The decision variables are the entry rule, the exit rule, the queuing rule, the information rule, and they also use the steady state probability, those PI values, as decision variables. And one may wonder why is this good? Because, as was mentioned, the steady state probabilities result from all the other rules. So they are sort of a result and not independent variables that I can directly choose, and they were mainly used for the purpose of providing the proof, but I think it's not just this. So in a system where we have positive externalities, then sometimes, well, it's not directly connected, but in the system, the current one, sometimes my incentive to join the system increases when I know that more others join the system. Like because the service rate will be higher. And in a paper by Moshe Aviv and myself, we call this follow the crowd, FTC property. So the more other people use to take some action, the more I'm inclined to take this action, in our case, joining the queue or staying in the queue. And under this assumption, when we have follow the crowd situation, typically the equilibrium is not unique. And I think in the current model, if we only use the decision variables, entry, exit, queuing, and information rules, it's quite plausible that the resulting equilibrium, that means there is more than one solution that satisfies the balance equations and the incentive compatibility requirements. Now, what the authors do here is they show that under the rules like the first come, first served, and the no information, etc., there are steady state probabilities that are compatible with the optimal solutions, but it doesn't mean that just the different rules always induce these steady state probabilities uniquely. I suspect that the solution need not be unique. So taking the probabilities as the decision variables actually correct the situation, but of course, not direct decision rules, and maybe there is needed some other rule to guarantee that the equilibrium we get is what we want and not a different one. This is something that has to be verified. Finally, about the first come, first served regime, I think the choice of the terminology first come, first served is not good. Indeed, it generalizes first come, first served in very simple models, but not always. And it's quite different from what one may have intuitively when we say first come, first served. For example, consider a server like a cook in a restaurant, a receptionist, or a medical doctor who serves the customers and sees the queue length. And when this server sees a longer queue length, then it's natural to start serving more quickly. There is some pressure, and I see many people are waiting, so I provide fast service. But here, first come, first served means that the whole service, the faster service, is dedicated to the first person in the queue. And this is not the situation in the current paper. The current paper has this beautiful thing that is more related to what's called discriminatory processor sharing. Actually, what the authors called zero, service in random order, is, I think, exactly what is called EPS, egalitarian processor sharing, that all customers get the service at the same rate. And the more general thing is when the service rate is allocated according to some priorities. And in our paper, in this paper, the priorities are not attached to customer types, but attached to customer positions. So the customer position I obtains service at rate μi minus 1, which has a great property that the expected time to stay until you finish, until your service is completed, is independent of future arrivals. So I think this regime is new. I have never seen another paper with this regime. I think it has this beautiful property of independence of the future, but I would look for a different terminology rather than first come, first served. I don't know, it's some type of processor sharing, position-dependent processor sharing. Maybe not the best sequence of words, but something like it, I think. So to conclude, as I said, this paper has several new features, and it's very nice to have even one new feature in a paper, and here there are several of them. And I hope that my comments will help to marginally improve the presentation, at least. Thank you.
Thanks a lot, Rafi. I think now we can keep going. So Yeon-Koo, Olivier, if you want to reply, feel free. And also others, if you want to participate and ask questions after the reply of Olivier and Yeon-Koo. Do not hesitate. It's, as I said, we have no time constraint.
So first of all, thanks a lot, Rafi, for the wonderful discussion. I mean, it's really nice. And also there are many papers that I actually don't know, so I will dig into this. And this is super useful. There are many questions that you asked, so maybe we can spend some time discussing. I don't know what's the exact time we have, but on the last question, I think we, with Yeon-Koo, we tried to think about, first come, first serve, and the definition of first come, first serve, and how it eventually boils down to the service rate where, the rate at which an agent is served when his position L is basically μL minus μL minus 1. And so we have another note where we try to think about first come, first serve as a rule where, let's say the queue length is kept, and the designer wants to maximize a weighted sum of QL, okay, so for each L from 1 to cap. And he puts higher weights on small l. The weights are like decreasing in L. This, let's think that he's doing this subject to feasibility constraints. Then we show that if the service rate is increasing concave, then first come, first serve is work conserving. And beyond this, it gives you exactly this definition of the service rate, μL minus μL minus 1. So the definition is that we implicitly use, but it's not explicit in the paper at all. It's like we maximizing this an objective subject to feasibility constraints, and the objective is really maximizing a weighted sum of service rate, where you put higher weights on position 1, and then higher. And it's going to be decreasing as the position increases.
So Olivier, I think that part of the issue was that the version that Rafi saw, didn't have this feasibility.
Exactly. No, I see.
Stated, and so this example that Rafi gives in his slide, in fact, it's actually doesn't apply to us because this hotel receptionist, whatever, right? So we have this feasibility constraint saying basically that for a set of any K agents, there is this maximal service rate that can be allocated to any one of them, right? And we have this constraint, and what that means is that the rule that we specify, that we define to be first come, first serve, does actually maximize the service rate going to the first guy, subject to the feasibility constraint. So this is also seen from how our rule applies to the dynamic matching setup. It's basically that you try to maximize the matching probability to somebody who arrived first. And then only when he cannot be matched, you move to the next guy, right? So this is exactly what we do. And so what we are saying is that the first come, first serve that we define is indeed truly first come, first serve in all the situations. The only situation where there is some bit of issue is that if mu service rate process doesn't satisfy, let's say, the regularity constraint, then it turns out that the first come first serve we define may not be work conserving. So this is sort of one issue that you are hinting at in your slide. In fact, this can happen. And this is why it's important for us to invoke and assume the regularity condition, because that does imply, in fact, that, given this rule, our definition of first come first serve is really truly the rule that maximizes the service rate in the order of arrival time, actually. So, yeah.
I wonder if your model doesn't, the definition of your model doesn't include the example of the cook that I gave?
So I don't know exactly what that example works, but let's say that if somebody can be served at the rate of 10, let's say, then the first guy will be served at the rate. There is no question about it.
No, but if the rate is event in the beginning 7 and then it increases to 10, then you can still serve this first person at rate 10 instead of 7.
So we can. I think we have a separate document that actually defines first come first serve based on the feasible rate, independent of this assumption about regularity. And what we show is that we could come up with an example, I think, which has kind of a flavor of your example, which violates regularity, and therefore the first come first serve we define is not work conserving, right? So trying to sort of maximize the priority to the first guy sometimes result in not being able to utilize all the services. You have to sort of leave some slack. You will have to have that. And so we thought that this is not an interesting phenomenon. So I think that by assuming, I think maybe work conservation assumption kills that example that you have. But in that case, we can independently define the first come first service rate allocation, which looks just like what we wrote down, except with a slightly different notation.
Rafi, can I comment on what you said? So the example is like mu1 is 7 and then mu2 is 10. Is it what you had in mind? Right? And then you're saying that you can serve the guy in position 1 at rate 10. Is it what you said? So this is actually not allowed, and I think this is an issue in the version you. This is something that maybe is not explicit in the version you send, but if you come back to the feasibility, maybe I should share my screen. Oops. Yeah.
I think it's not explicit.
Yes, you're right. You're entirely right. So in the slide,
written somewhere.
It should be.
So in
this is very basic.
Yeah. So in the slides, let me share my screen. Can I share my screen? Yes. Can you see my slides?
The first one.
So this condition says that, let's say you have only one guy in your example. So let's say only one guy. Then the rate at which this guy is served is at most mu1, which you write. I think is not there in what you read, but this is imposed. This is what we have in mind when we think about feasible queuing rules, and this is something we want to impose. And so meaning that if mu1 is 7, then you cannot, and mu2 is 10, then you cannot serve one guy at rate 10.
Right. So
you can serve it at most at rate 7.
Yeah. So mu1 applies to anybody, no matter how many people there are. For any individual, subset of a group. So mu1 applies to any single individual. Maximal service rate that applies to any single individual, no matter how many people there are. Right. It is possible, however, that if there are more people, you could serve additionally after exhausting this mu1 to the first guy. So if there are two guys, so if mu2 is like 10, that means that you can still at most serve at the rate of 7, the first guy, but then you have a 3 capacity left over.
I see the point. Yeah, I think it should be made more explicit. I didn't notice it.
You're entirely right. I think it's.
I didn't understand.
You're entirely right. We now have an explicit. Make this explicit in the new version. So you're entirely right. Yeah.
Somehow verbally to mention it. You're right.
And the other sort of a general thought that I had in terms of especially the objective. So I think there are many queuing papers that I've seen that actually try to think about profit maximization, but not in the sense that you are talking about, like, you kind of somehow monetize all the benefit that the consumers will have through some monetary fees. I think what they have in mind is some call center, maybe run in some India or some places that are subcontracting. So I have a subcontract to service run the customer centers to service as many people as possible with a given number of steps that they have, right? So this issue arises like in Japan and Korea when they're now trying to sort of schedule, COVID vaccination right now. So they are very understaffed, and the goal is to kind of maximize as many people as possible. And that sometimes is equivalent to the goal of minimizing the downtime, right? Because if the system goes idle, you are wasting this step member. So the goal is to sort of make the queue as long as possible, even though this may not be in the best interest of the agents. So this is what we mean by R. In some sense, R is the profit, kind of ostensibly we define to be the profit per customer served. So this is like I think the right way to think about it is the shadow value of serving each person. And so basically goal that we have in mind is to minimize the probability of the system going idle. So this is when alpha equals actually 0, right? So this is kind of what we have in mind when, this is a bit different from positive externalities that you talked about as a reason for trying to induce the agents to queue up as much as possible. So there are kind of some other maybe agency-related reason, right? So I'm subcontracting to run this system, and my goal is simply to maximize the utilization rate for the services because of the way the contract is set up, perhaps. Yeah.
I didn't object to this, and I think it's simpler. Your example on vaccination is good. If you take the vaccine, that other people gain from it. So there is benefit to the society or to the server. There are positive externalities. I didn't object to this. What I said is this is new, and this induces this assumption is associated with positive externalities. So these are the cases that the paper deals with.
Yeah, I think I fully agree that there is a positive externalities for that example. But even in the commercial setup, right? I think that the call center that is run often is run to maximize utilization, given the set of people that they hire. So even without there being explicit positive externalities, maybe the presence of positive externalities further reinforces and maybe underpins the reason why system is set up in this way. So there may be some more fundamental, profound reason having to do with positive externalities, but the casual observation seems to suggest that this is how the call centers are often run. So I think that we kind of take that as given. Yeah, but I think that it's useful to dig deeper into more fundamental reason. Yeah.
I actually have another question. The cutoff policy allows randomization at the value k minus 1. And I wonder, I think that the optimal policy is pure.
So actually we have a characterization, an exact characterization that of the optimal policy in the case where alpha is 0, meaning you put all the weight on the service provider. And in that case, generically, x k star minus 1 is interior. It's between 0 and 1. And let me explain why. So what you want to do when alpha is equal to 0, so meaning when you want to maximize service providers' profits, is intuitively, you already said that you want to have the longest possible queue in some sense, because you want to minimize the likelihood that the queue is empty. And beyond this, the service rate is increasing, so you will benefit with longer queues. So what the designer wants to do is to increase the queue length, so the maximum queue length. So what will happen is there is an integer issue, which is that at some cap k, what's going to happen is what the designer wants to do is to basically have the insertive constraint binding, right? He wants to increase the queue length so that the incentive constraints are binding. If it's too large, clearly the agents wouldn't be willing to join because the waiting time is too long in that.
Let me ask again, maybe it's a misunderstanding on my side. Suppose you can do whatever you want. You can tell people to join and to leave and so on. So the optimal solution will be a pure cutoff. There will be no randomization. Forget about incentive compatibility.
Oh, forget about incentive compatibility.
Forget about I can tell them to do what
in that case, it will be infinity. So we are dealing with the alpha equals 0, right?
No, but general alpha is between 0 and 1.
So the remark that Olivier made about the generic optimality of interior solution or rationing, if you will, applies to the case where alpha is either equal to 0 or very small. In other cases,
and incentive constraints are taking into account. Right?
Incentive constraints are not binding, then you are right. But in this case, so the idea is very simple.
What is the meaning of optimal? Optimal, you can forget about incentive constraints when you talk about optimal.
Right. That's exactly what you are trying to say, right? The alpha is a parameter. You can talk about optimal policy for any value of alpha. Let's fix alpha equal to 0, right?
Why 0? If fix alpha equal to half.
So I don't know whether this will happen or not, but so the claim is applies to when alpha is very, very small or 0, right? So we are trying to at least explain to you why the rationing is part of the optimal design, right? So start from the case where, let's say alpha equal to 0. Okay, alpha equals small is also possible.
Can I interrupt?
Ignore incentive constraint altogether. You will run on infinite. Oh, yeah, alpha must be exactly equal to 0, I think.
So can I interrupt 1 second? I think Rafi is considering an optimal solution where there is no incentive constraints at all.
That's right.
So then
first best.
Yeah, so first best, but then it's not going to be achieved.
No. It's actually so there are two things that are relevant. If what you are talking about is a situation where incentive constraint is not going, IR is not going to be binding, yes, it doesn't involve any rationing. Now, think about a situation where IR is binding.
So I think Rafi wants to forget about,
ignoring the incentive results in the violation of IR, right? So I think that we have to say that, when you ignore the incentive, yes, the cutoff is optimal. And in particular, when alpha equals 0, running an infinite queue is optimal, okay? But that will violate the IR and IC for that reason, okay? So if you if you keep the cap maximal size to be, let's say 10, then maybe it's too long and then they will suffer loss. So it will not work. It will not be incentive compatibility. If you reduce it to 9, now it could work, but then they have strict incentives. So that's why
it's second best, but it's second best.
That's right. That's right.
Optimal subject to incentive compatibility.
That's right. So the claim is that but remember our relaxed problem is devoid of incentive constraint largely, but it's not completely devoid of incentive constraint. We still retain the weak form of incentive constraint, what we call individual rationality, right?
And I understand.
Yeah.
Okay, thank you.
So just one additional comment. There was many comments. So you had an example where cutoff policy is actually not optimal. So you have this where the mu-k must not be concave in your example. Yes. So I think just a small comment on this. Eventually, our result holds even if you don't have cutoff policy. We have a side remark on this, where as long as if you think about the let's call the effective arrival rate just lambda k, which is the arrival rate times xk, the entry rate. Okay, and you could think about the effective removal rate as mu k plus yk, for instance. Okay. And then if you think about these effective rates, and our result holds as long as on these effective rates regularity holds. So even if xk is not a cutoff, as long as the induced, so just a side remark, And your example will fail this, but it's a nice example. Yeah.
And the other thing is that given the regularity condition, the cutoff policy uniquely pins down P. So there is no possibility. And you are right, however, that this is the reason why we also retain P, the invariant distribution, in a situation like that as part of the choice variable, because otherwise optimization problem may not be well defined. And so this is very common in the principal agent model, because you have all the control, which is the contract schemes that you choose, but the induced behavior on the part of the agent, there may be multiplicity. And so we give then the designer the extra degree of freedom in terms of breaking tie in favor of him, just to make the optimization problem well defined. And so
I would add a discussion to this, make it explicit.
Yeah. No, I didn't know follow the crowd. I mean, I should look at your papers on this. But one issue we have in mind is you have multiple invariant distribution, is that the solution that the designer selects is a solution which puts zero weight on state 0, for instance. So this is going to be an issue if we have this as an optimal solution. But what our result shows is that eventually, given that we have a cutoff policy, the invariant distribution that the designer will eventually select will put positive weight on 0. So in this sense, multiple solutions.
Just to be clear, I think this issue arises possibly when the regularity fails, right? So when the regularity holds, basically the optimal cutoff policy induces P precisely. There is no multiplicity.
But among the policies that the designer can allow, he can allow in particular policies with multiple invariant distributions, some which will put 0 weight on on state 0.
True.
But at the optimal solution, it turns out that the optimal solution is one where there is positive weight on 0, and then this invariant distribution is actually meaningful. And so, I'm sure we're missing many of the
I didn't keep track of everything very clearly.
But it would be great if you could send us your slides and
that would be nice actually. There are some
I will mail them.
Thank you.
Yeah, we will send you also the chat with the questions and the reply from Yeon-Koo. And you
thank you.
Information about what happened during the. I think Yeon-Koo, you didn't hear me. I just said we will send you also the chat with all the text file with all the conversation in the chat, so you will get all the questions and all the reply that you gave. So you have.
Thanks.
You can keep it. Okay. If there is no other questions, just one thing to say. I'm going to announce the next talk, which is in 2 weeks, on the 7th of June. We will have the pleasure to welcome Matt Jackson from Stanford University. We'll talk about learning through the web ring, the impact of noise, and the breadth and depth of social networks. Is there any other questions or discussions? Okay, if no, thanks a lot, Rafi, Yeon-Koo, and Olivier. That was great. It was a great talk and a lot of interaction. So I think we all learned a lot.